Our next speaker is Sewen, and he's going to speak about adventure of a lifetime, extract method refactoring for Rust.
So, hi everyone. Can you hear me? So today I'm going to talk about extract method refactoring for Rust. My name is Sewen, and this is joint work with these lovely people. To get started, let's extract a method in Python. So here we have a program which manipulates two lists with some aliasing and then print the value of z here afterwards. We want to extract this conditional branch, which will assign the value of z a local variable y in one branch and a global one in the other. So let's extract it, produce something, let's run it, and it works. Now, let's try a similar program in Rust. This is just where we made all the references more explicit. So let's try it. It produces something down here. Let's run. And oh no, it didn't work. The compiler is complaining. So extracting a function in Rust is actually non-trivial. Why is that? What are the challenges of extracting a function in Rust? So in Rust type system, every value has an owner. And there is a set of rules to allow other entities like a function to use the value by borrowing or taking ownership of it. And in extracting a function, we need to take those rules into account and make the borrows explicit. So the extracted function has the necessary permission to complete operations like mutating a string. And those borrows have lifetime, which we've heard something about in the previous talk. This is how Rust type system calculates something similar to a scope. This is done using what is called the borrow checker, and it allows Rust to safely manage memory at compile time. This avoids things like dangling pointers by making sure that the pointer references a value with the same lifetime. Another challenge that we faced, but I won't go into detail, is we had to propagate the non-local control flow, and it wasn't done well in IntelliJ, which we built on top of. So one important observation is that the extracted function just now is actually almost correct. If you give this to a Rust developer, they would simply correct the level of borrows and ownership, and then add some lifetime annotation, and then we'd have a extracted code that is acceptable by the compiler. So our main point is actually Rust extract method refactoring is a repair problem. We just need to apply the patches in the correct order. So we have implemented our solution rem to do specifically that. So we start with the normal IDE extraction, where a developer would use the UI and then get a hoisted function with a call site where the function body was. And then this is where, in cases like Python, the extraction is successful and we can stop. But for us, this is not enough. The hoisted function is still broken. So now we start our refactoring as a repair pipeline, where we first fix any non-local control flow. We then do a static analysis to determine the level of ownership and borrow that the extracted function needs. And finally, we set up the initial lifetime annotation in the extracted function and use an oracle to determine the fixes to those annotations. So let's go back to our example in the beginning and go through the pipeline step by step. So first we hoisted the function, and we see that it doesn't work yet. We're here now. Skipping the non-local control flow fix, we now have to do some static analysis on the caller and the extracted function. We collect constraints about usages, aliases, mutability, and definitions, and then we use Prolog to solve those constraints, determining whether the extracted function needs to borrow the value or it needs to own it. Briefly, we see here that y is aliased by z, and since we use z, we need to also be using y, and therefore the function needs to borrow y and not take ownership of it. We patch the call site to borrow y, and then we patch the signature as well as the extracted function body to treat y as a borrow. So after we patch the necessary borrows, we need to give those borrows lifetime annotation. We start by annotating all the borrows with unique lifetime, meaning that we initially expect all of them to have different scopes. We start with LT0 for the first input reference xref up until LT3 for the output lifetime. And now we need to ask an oracle. Here we're using cargo check to invoke the borrow checker to see if our annotations are actually correct. If cargo check fail, it'll give us a way to relate the lifetime together. That means for the function to be safe, the borrow checker needs the lifetime to be bounded together, i.e. like lifetime 1 needs to live at least as long as lifetime 2. In this case, since in one branch we return y as a borrow, we need to make sure that the input lifetime for y, which is LT2, is related to the output lifetime LT3, and the borrow checker tells us exactly that. So we add this bound, and now we have an extracted method in Rust. Let's do a demo of that, which is using our own solution. Yeah. Okay. That is weird. There we go. And we have this extraction, which is apparently not working. Sorry, give me a second. Oh, there we go. It was just happening on my screen and not on the shared screen, sorry. So let's run it. And voila, we have our extraction. Yeah, sorry, there was a bunch of prompt that was happening on my screen and not the actual slides. So here, we have the demo. So now let's see how REM did. We evaluate REM using 3 research questions. So is it practical? That is, can it produce good extraction most of the time? And will the code that it produced be similar to that of a Rust developer? And is it efficient? How long do we wait on average for an extraction? And 3, we compare it to existing implementations, which are the IntelliJ Vanilla plugin that we built on top of, and also the Rust Analyzer plugin for VS Code. We run 40 extraction on 5 real-world projects that are quite popular. And we covered a variety of code features in the extraction, such as extracting breaks and continue from loops and extracting returns. We also extracted function that requires mutable and immutable borrows. We extracted function that needs to have its lifetime annotated. And we also extracted function that uses structs that have lifetime slots in them. We do 3 types of extraction. We inline existing function, and then we re-extract it using REM. We also do random extraction, and then we try to go through version control to find where developers have actually done extractions and try to redo that with REM. There are 3 outcomes. Good extraction produce compilable code. Bad extraction produce non-compilable code. And no extraction means that the tool recognizes it cannot extract and then informs the user. So this is our result. Let's dive a bit deeper. So is it practical? REM produced good extraction in 37 out of the 40 cases that we had. And in the 3 cases where we couldn't, we informed the user. And the extracted code is similar to the developer version with some minor caveats. So let's look closer at experiment 19, where we inline the decode function and then re-extract it. There's only 1 lifetime specified in the developer version, so the borrow checker expects everything to have the same scope. In REM's version, the lifetime is bounded a bit looser. It is more permissive because our repair process actually only bounds the necessary lifetime together enough so that the function is safe. And here we can technically have the borrow I with lifetime LT0 being dropped before the borrows in T1 and T2 with lifetime LT1. But in the developer version, I must live as long as T1 and T2. So in this case, I think REM is practical. And on average, REM takes about 1 second to produce extractions. We found that using cargo check is actually not the end of the world. Once the project is compiled once, the check is only done on the modified file. And while IntelliJ and VS Code produce extraction instantaneously, I think this is still a good enough efficiency for us to use during development. And even in our worst case, where we needed 3 Oracle invocations, we only took around 2 seconds. And our implementation efficiency actually varies more with cargo check cycle than it does with the project or file size. So yes, REM is also efficient enough. And while we successfully refactor most of our cases, IntelliJ and VS Code completed about 50% of them, with notably IntelliJ and VS Code failing on lifetime-related refactorings, and IntelliJ also sometimes fails on the borrows as well. So it is more effective in that sense. And there are some limitations of REM. So first, we don't support generic trait bounding. We can probably apply the same repair that we use for lifetime, but it needs to be reasoned about more. And we also currently rely on IntelliJ for type inference that we use for our borrow analysis. And IntelliJ like to re-implement what the compiler does and be just on its own, standalone. So if anything were to be discrepancy between them, we also have that. And for further work, since our pipeline is mostly in Rust, we can basically have a front end for VS Code for Rust Analyzer to use. And we can also need support extracting trait bounds and other features. So to conclude, we found that extracting a function in Rust is non-trivial. But refactoring in such a complex file system can be decomposed into a series of modular repair problems which are easier to solve. And we implemented this idea as a robust and efficient plugin. Thank you.
Hi, thanks for the talk. So suppose you've got a novice Rust programmer, and they're doing some Rust programming, and they've got some errors that they're not sure how to resolve. Could they take your modular repair mechanism and apply it to their code and hope that it might help them with their misunderstanding of Rust situation?
That's a good question. One of our limitations as well is that we require the project to be in a compilable state, but there is something that we can do to remediate that. We need to basically kind of mock the environment so that it is somewhat compilable. But in that sense, I don't think it would actually provide the feedback that the Rust developer need to fix their problem. It would just help with the extraction.
It would just help, say again?
It would just help with the extraction process, yeah.
But it seems like you first extract and then you do a bunch of fixes.
Yeah.
So could you take those fixes and apply to something that didn't result from an extraction?
Yeah, I see what you mean. Yes, because our pipeline is actually decoupled. We have actually 3 different binaries in Rust for that, and you can technically apply those into the program, and then it would result in some fixes. It may not be, because we apply them in the context of the refactoring, and we kind of know what is expected before and after.
Sure.
So I'm not sure how it would play out in a
Thank you.
random piece. Good.
This is very cool, but it's also quite complicated. Do you have any thoughts on choices the Rust language designers might have made to make this kind of refactoring simpler? How could language design have been changed to make this a little less painful?
That's a very interesting question. I'm not sure, because this was mainly a feature for safety, for memory safety, which, as we learned from the previous presentation, is complex because otherwise it would cause a lot of problem like in C. I'm not entirely sure if there's a better solution to do this that would make it less painful, but yeah, I don't see it as avoidable.
Thanks for a cool talk. How feasible do you think it would be to avoid all these many different lifetimes on the extracted method and collapse some of them in a way that the programmer seems to have done?
So sorry, could you repeat that?
Yeah, sure. How feasible would you do you think it is to sort of avoid having all these extra lifetimes and extra bounds and collapse some of them, even though it makes it a bit less general?
So this is already collapsed, and we can kind of collapse it further and constrain it further. But we were trying to constrain the amount of time we try to invoke the oracle, because the more constrained that we are, we actually might need to loosen it back so that it compiles. So yes, it is possible. It just probably will require a few more invocations.
Thanks.
Hi. So is there any completeness argument on refactorings, like in terms of lifetime inference? Is there any completeness argument with respect to refactoring?
I'm not entirely sure.
Okay.
In terms of like,
So lifetime inference is something which is also done in, for instance, region-based memory management, right? So you could have principal typing, which means that there is a principal lifetime allocation for variables. So in that sense, is there like a principal, like do you know when you have converged, for instance?
we tried that approach, but the problem is that actually the current Rust type system is not fully formalized yet. We have Polonius, but it's not completed. Okay. So it's hard to actually have a principled approach to fix the lifetime. That's why we kind of decoupled it, so that we have principled approach to fix the local control flow, the ownership, but we couldn't really do it for the lifetime. So that's why we used the repairs instead.
Okay.
Thank you.
Okay, let's thank the speaker again.